2.1 rational functions, identifying holes and asymptotes in functions that are rational. And we are going to make the assumption, so as you can see here, so we have f of x is equal to, now I used n of x over d of x, and that's just, numerator and denominator. I mean, typically we may not really use n because we use n for counting, but not a big deal. So we're going to make the assumption that both n of x and d of x are just polynomials. All right. Now, polynomials, as you know, you can sometimes factor them out, try to find all the zeros of them. Sometimes they don't have any. So it will just depend on how nice they are. But there are pretty interesting things that you can find out from these rational functions. In particular, if you're trying to sketch them, or if you want to know some characteristics of them, when they have a hole and then when they have an asymptote. Okay, and you'll see, I guess, what the hole means. It means, well, it's a hole. It's kind of a place where the function is not defined at that particular point. Okay, so it has a hole in the actual function if you would be sketching it out for yourself. Now, the asymptotes that you have covered in the past, okay, so with respect to asymptotes on numerous occasions in various videos, this is intended for advanced functions, so someone who's in grade 12. So the assumption is you had kind of grade 10 and grade 11 functions, and then now you're kind of extrapolating on that and learning. So let's take a look at this breakdown, and I'm going to try to show you through examples what this hole actually means. So you have kind of an empty space at a particular point. We'll start with that, and then we'll try to knock off the asymptotes, both vertical asymptotes, then there's horizontal asymptotes, and then there's kind of slant asymptotes. So like lines which are basically have some kind of a slope, which is, not zero, and not undefined, which is vertical. All right, so the first idea, and again, this is all for the assumption that n of x and d of x are polynomials. So f of x is a rational function, but made up of two polynomials. All right. Now, if you find out that, for instance, you'll take your numerator, so that polynomial, and then you take your denominator, and they have a common factor. So some, let's say, x minus a. So basically that would mean that it's a zero, right, for n of x and then for d of x at a. And now when you take that and you find out, you substitute it into your function, you get this indeterminate result of 0 over 0, which makes sense because if they have the same factor, right, x minus a, and that's on top, and then you have x minus a at the bottom, you substitute a, you're going to get a minus a, which is going to be 0. And then anything else there doesn't really matter. It's going to cancel out. And then the same thing you'll have in the denominator. So you have 0 over 0. You will find that at a, okay, you will have something which we call a hole. So let me show you this through an example, and then we'll kind of plot it out. So I'm going to try to show you first a rather simple one. So let's say here is my example, okay, and this is what's going to lead into a hole. So let's say I have f of x, okay. Now we're supposed to have a polynomial over a polynomial, right? So that's what we're supposed to have on top and the bottom. And in this particular case, let's say I have x minus 1 on top, all right, and then I have another polynomial, and I'll put it in factored form just so that it's easy for us to see. So x minus 1, and let's say I have x, plus 2. Okay, so I have something like that. Now, in this particular case, so what we have is they have exactly the same factor, right? If we were trying to simplify this, then what we would get is those two would cancel, and then we would get 1 all over x plus 2 as our final result. But as we know, just because those two factored, if it's a function, for a function for our input, that factor of x minus 1 just doesn't disappear. Like, sure, it's going to look very similar to this, okay? So that's kind of how it's going to look like, which is 1 over x plus 2. But, if we substitute x is equal to 1, In this case, what we would get is we would get 0 on top, and then you would get 0, right, multiplied by, it's 1, so it's going to be 3, which is still 0 over 0. So that means that we get an indeterminate form. So at x is equal to 1, this function, at 1, that's not part of the domain, so it doesn't really exist. Now, if we would sketch this out, so 1 over, x plus 2, okay, so if you're thinking about this, now you may remember, so 1 over x, that's the actual parent, right? And then we just have a shift, so x plus 2, which I guess is, minus 2, so it would have shifted it to the left. So this would look kind of like this. So let me sketch this out for you. So if I have it like that, okay, so we know that 1 over x, okay, and then so within here, so we would have had, would have looked like that, and then it would look like that, but because of the x plus 2, so this thing is going to shift over into here, and really what this would have looked like is kind of like this, right, and then this is like that. Then we would have some kind of a vertical asymptote, which we'll talk about shortly, but moreover, at x is equal to 1, so at some point 1 right here, we basically have a hole. So it doesn't exist there. So this would look, nice and smooth, but then at that particular point we have a hole, right? There's a discontinuity that happens there. And let's plot this out so that you can see it. And then, you will see that in Desmos. So I'm going to bring up Desmos, okay, on the side here. And let's plot it out. So we have f of x is equal to, so x minus 1 all over. This would be x minus 1, and then x, let's say, I guess, plus 2. So this is exactly what we sketched out. So that's not a surprise to us. All right, so this is what we have. But, okay, notice that if we try, okay, to go along here at 1, notice that it shows us that it's undefined, right? There's a hole there, okay, because of the fact that we have that x minus 1 on top and x minus 1 at the bottom. So this is one interesting aspect that actually happens with respect to these rational functions. So if you have this rational function, okay, and you find that you have the polynomial on top and polynomial at the bottom, and when you substitute it at a particular point and you get 0 over 0, it will result in a hole, okay, on your plot. All right, so that's something that you can think about. So those are holes, right, where they're just kind of empty, nothing is defined for that. Let's take a look at the second item. So the second item, which is this one, if your function, okay, so f of x, it will have a vertical asymptote, okay, so it will have a vertical asymptote. So that means you're going to have a nice asymptote, okay, which is vertical, and it's going to happen at, I guess, some a, if when you substitute a into your function, you're going to get your numerator, right, which is going to be non-zero, divided by your denominator, which will be 0. So really what that means is that your denominator has a 0 at a. And if it has a 0 at a, we know that that function is undefined there. But moreover, okay, if your numerator, so your polynomial on top, is non-zero, okay, so it is defined for a, then it creates this vertical asymptote. And we actually saw this with exactly the same function right here. So we had a hole at x is equal to 1, but then notice that at x is equal to, so in this case, minus 2, so for this function, if I remove this, we already know that there's a hole. I've sketched it because we can relate it back to our parent function 1 over x, okay? But moreover, even if it wasn't, 1 over x as our parent, if it was something else, okay, that was different, we could have had more items on top or possibly at the bottom. So in that case, because, okay, if I substitute it here at -2, what we would see is we would basically get, this is going to be 1 regardless, because the x minus 1 is going to cancel. And then in here, we're going to get 0, right? Now, if that happens, that means that we have an asymptote, and we do, right, at that particular point. Okay, so vertical asymptote, whenever your denominator is 0, but your numerator is not, for these rational polynomial functions. And that could have happened, so notice, you could have done something like this. I mean, we could have complicated this, even further. Let's say if we had x plus 3 here, and then this is going to be all over. So let's say it was x minus 1 and then x plus 2. So in this case, clearly this is no longer a parent function, right? 1 over x, because we added that x over 3 in the numerator. But we still have a 0, okay, in here in the denominator at negative 2. So x is equal to negative 2. And now, so let's see that. So I'm going to, again, bring out the decimals. Okay, and if I would bring out decimals, then we would sketch this. So let's, so change this function here. Okay, and I'm going to put x, I guess it was plus 3. Now, it doesn't really matter what we would have put in there. So notice that we still have exactly the same asymptote. And in this case, if I squeeze this out a little further, we can see that it happens at negative 2. So our function is approaching from both directions, okay, into that vertical asymptote. So that's pretty neat to be able to know, and it happens for any. So if I had, so if I go back here, and let's go back and try to get in there in the denominator. So let's say if I added something else, and I don't know, let's put maybe, x, and let's say minus about 3, okay? So we'll do that. So now in this case, we actually have 2 zeros in the denominator. We have 1 at negative 2, so we have an asymptote there, which we see actually on the screen, but we don't see another one, so notice this is going to be at 3. So based on what we just stated, okay, that means there should be another vertical asymptote there. And indeed, notice if I go in here, this is exactly what's going to happen. So I have another vertical asymptote at 3. And you can keep playing that, and it's going to be interesting because it's going to make these things more and more complicated, right? So let's say if I shift one even further, right? So now, okay, so look what's starting to happen. Like these functions look terrible, but whatever. Okay, so we have a vertical asymptote at negative 2. We also have another vertical asymptote at 3, okay, right here where the blow up happens. But now I've added, I think it was negative 5, was it? Let me just check. Yeah, so that means I have another one there. And you can keep going. You can have more and more of those zeros. If you get stuck, and your teachers are mean to you and you have a polynomial on top and polynomial at the bottom and it's not factored out, then unfortunately you do have to go through kind of factoring out. So you can use the remainder theorem or any other method that you like. I did the video on kind of factoring out for advanced functions. I'll put up that video up above there for you. Okay, so let's come back here to our notes. So I'm going to squeeze out the decimals on the right hand side, okay, and let's go back in here. So we've covered 2. So we have holes, right, where we have indeterminate 0 over 0 happening in our function, rational function. We have vertical asymptotes whenever we find our zeros in the denominator, okay, so we have an undefined result. And now if you squeeze out, okay, and notice, so here are horizontal asymptotes. Okay, now horizontal asymptotes means that we have flat lines, right, in some kind of a form. So those are horizontal asymptotes. Now, these only happen when the degree of the numerator, so the degree of the numerator, polynomial, is less than or equal to the degree of the denominator. So that's kind of important. And to be honest, I mean, if you're doing your tests and things like that, you might have to kind of remember. But these are things I even look back because I don't remember these things because you don't use them often enough. But for sketches, it's nice to be like, oh yeah, for rational functions, when were these asymptotes happening? So for horizontal ones, again, your numerator, okay, the degree of the numerator is less than or equal to the degree of the denominator. All right, so that's something that you can think about. So like, I mean, I guess I can capture it here, you know, so the degree of the numerator has to be less than or equal to the degree of the denominator, right? And these are degrees, right? So this is the degree of that. Okay, so the degree of this is less than, okay, than that. So now let's see that happening, right? Let's see that happening. We just did, okay, a pretty complicated result for us. So we had a numerator. So notice you can still see it there in decimals. Okay, so I'm going to try. Let's see if I can, you know, go in here and so that we can see the whole thing. I mean, we don't need it that far. Let's not make it that complicated, but just so that we can see this. So then the numerator, the degree of the numerator is 2, right? Because we have x minus 1 times x plus 3. So if we would expand it out, we know that the highest degree in the numerator would have been 2. The degree of the denominator is actually 3, right? If we would expand that out, we would have to get a degree of 3. So this thing applies. So that means there should be a horizontal asymptote for this particular function. So there should be something of a horizontal asymptote somewhere, okay, on the positive or the negative sides. Now, how do you find that, right? Like, how do you find like what it is? Well, if the degree in the denominator is bigger, right, than the one on top. Think about if you started to substitute for x and you made x bigger and bigger and bigger, so it would get eventually really big. Those minus 1s plus 3s and, you know, plus 2s that you have there, if x was, let's say, 1,000,000, then it doesn't really matter, right? And what happens is that your denominator, if it has a higher degree, for big x values, both positive or negative, it's going to dominate because, let's say in this case, you have a square on top, okay, because it's degree 2, and you would have a cubic at the bottom, so that's degree 3. And if you would cube 1,000,000 and you would square 1,000,000, you know, then basically what would happen is that the denominator would just dominate entirely. And you would see that the function goes to 0. So when the denominator is bigger, okay, you're going to see a horizontal asymptote at 0. And let's see this, okay? We're going to try to span this out, and this is exactly what happens here, right? So you have, so notice that the function's on the left-hand side, okay? It just kind of goes in, and then it follows down, okay? But if we would zoom out on this, okay, so notice within here, let's see, we can push this out. Okay, so let's see what happens. So we have a horizontal asymptote there. Okay, so it's kind of skewed down and looks like it's a little bit below. Okay, so within here, yeah, so we have this, and we can see that it's kind of happening within. So it's on that side, and then if I go back over here, okay, so notice that in here, okay, so it basically just tries to tend towards 0. All right. So that's what happens in these two instances. Okay, so we have a horizontal asymptote, okay, on the right-hand side, and it looks like we have one on the left-hand side as well. All right, and now in fact, okay, so if I would substitute f, okay, at, you know, let's say, notice what value we're getting. So if I'm substituting f at, you know, 1,000, notice that it's getting to 0. Okay, 10,000, it's just getting smaller and smaller and smaller. So you can see those values. Now it's scientific notation. Okay, now if I would substitute negative values, so we're going to get, okay, so notice what we're going to be getting. So it's getting, so it basically goes below, okay, so it goes below 0, but then as you get bigger and bigger, then it starts to come back towards 0, more and more and more. Okay, so it dips below, and then it just, the asymptote is still there at 0. Okay, so it just will tend towards that. So that's your horizontal asymptote. And now, so I'm going to just show you another example with respect to asymptotes. Okay, so let's say if it was something much simpler. So we have f of x. Okay, I'll give you a new example. And let's say that this was 2x plus 1, okay, all over. So this one, the top one is of degree 1. And let's make this one. So they're going to have exactly the same. Let's say this would be 3, okay, x minus 2. All right, and that is my rational function. So what would be, what could we deduce from here, right? What, in terms of the asymptotes? So we know we're going to have a vertical asymptote, okay, because there's going to be a 0 in the denominator. So it looks like it's going to be at 2 over 3. So there's going to be a vertical asymptote there at 2 over 3. Okay, fine. Okay, so that's great. Do we have any holes? Okay, doesn't look like it, because if you take the numerator and then the denominator, they don't have any factor in common. Okay, so there are no holes there. Now, are there horizontal asymptotes? And the answer is yes, because, so notice that here, if the degree of the numerator is less than or equal to, then we have a horizontal asymptote. And in this case, the degree is 1 on the numerator and denominator. And now, okay, so if you tend x and you push it towards infinity, so it gets bigger and bigger and bigger, okay, so you start substituting bigger numbers, these you basically ignore. And then, so if you ignore these as x gets bigger and bigger, then really this is just 2x over 3. It's going to start approaching this. So the x and the x cancels. So it looks like this is going to be approaching 2 over 3. So you're going to have a horizontal asymptote, okay, on the right-hand side, on the positive side. Now, on the negative side, what we're going to get is we're going to have 2x over 3x, and this is negative. So again, the x's will cancel, and still this will tend towards 2 over 3. So we're going to have this horizontal asymptote all the way throughout. All right? Okay, and let's take a look. Let's graph it out for ourselves on Desmos. And here, we're going to cover this up. Okay, and then let's remove that. So this is our new one. Okay, I'll just call it g of x just so that it's different. So we have 2x. I'm putting it in brackets so I can nicely put it in Desmos. 3x minus 2. I don't need brackets there, but so we said we should have a vertical at 2 over 3. Okay, so let's see if that is true. So yeah, it looks like it. Okay, so notice that this is going to be tending towards 2 over 3, which is, I guess, 0.66666, etc. Okay, so here's our vertical asymptote. And then our horizontal asymptote. So notice in here, okay, notice that it just keeps tending and it gets smaller and smaller and smaller. So let's do it. So g at, let's say, and okay, I'm going to make this bigger and bigger just so that you can see. Notice what it's tending towards. It's supposed to be 2 over 3, right? Which is 0.66666. And there you have it. Notice that it's just going straight to that. And then the same thing, okay, if I, oh, that's not what I wanted. I just killed it. Okay, so if I did it from the negative side, we would have seen exactly the same thing. All right. So that's something for yourself. You can check it out. It's going to be exactly the same. Now, there's one other item for these rational functions. So it's kind of like a special case. This is not always discussed. Okay, it's a special case because we have these slant asymptotes. So meaning, it's going to be something on a slant, like an asymptote like this, where your function is kind of approaching that, or maybe approaching that, or it could be, also a slant on the net with a negative. Okay, so it could be this, and then maybe, your function's kind of going like this, and then it starts to approach that slant asymptote. So when does that happen? Okay, so that happens when the degree of the numerator is greater by exactly 1, okay, from the degree of the denominator. So if the degree of the numerator is, let's say, 3, and that means that the denominator would have to be of degree 2, okay? In that case, you're going to get a nice slant asymptote, which should make sense to you. Because if it's 1 degree higher, then basically as your x tends towards a very big number, you're basically tending toward a line with some slope from both of the directions. So if I would do that, so I'm just going to show you here, say h of x. So this is our last example. So equals, so let's make it so 1 degree higher, all right? And now I'm going to put, actually let's put just a random, okay? So let's say x to the 3, okay? Let's say plus 2, all right? So we're going to do that. So that's going to be our numerator, okay? All over. Now we need it to be 1 less, okay? If it's 1 less, we're going to get that slant. Okay, so now 1 less, that means it has to be some kind of a quadratic. So x, let's say squared. Let's make it even complicated, 3x or something like that, minus 1. And notice the slant. Notice the slant. Like if I zoom in here, like look, do you see that line? That's your slant asymptote, okay? And you can even tell that the slant asymptote is, I guess, 2 over 4, right? Because you take the highest degree, you take whatever that coefficient is, so 2 over 4, which is 1/2, okay? And then that's what you would get. So that is super neat to be able to, to see that happening, okay? So there you have it. Okay, so that's pretty interesting in terms of what happens with these rational functions and how you can identify various asymptotes and when you have holes in your graphs. All right, thanks for watching. See you in a future video. Cheers, everybody.